So, oh, okay, great. So hi everyone. Thank you so much for joining us for our workshop number 1 of our Intro to AI Medicine workshop series tonight. So just a quick intro. My name is Olivia, and I'm part of the UBC AI Medical Student Society here. We've done this workshop series this past fall, and that one was mostly scheduled to accommodate participants from the East Coast. For this workshop series, we've tried to schedule it to accommodate participants from the West Coast, so like from UBC. So for those of you who are joining us from somewhere other than Vancouver, I apologize for the awkward timing, but thank you again for taking an interest in joining us for this workshop. I guess before I introduce our star instructor for this course, I just want to get some housekeeping out of the way. So just a reminder that our workshop number 2 will be on understanding the characteristics of data, and it'll be held on Tuesday, March 16th. So not next Tuesday, but 2 Tuesdays from now. For those of you who are unable to make specific workshops, you can send me a quick email. These sessions are recorded, so I can send them to you as well. We also have our workshop sessions from our from the last fall recorded and posted on our YouTube channel if you're interested, but I guess we've kind of revised the course a little bit and tried to improve it, so it might be a little bit different. Okay, so moving on to finally introducing our instructor for this workshop series. So we have Ricky Hu here. He's actually a UBC alumnus, so he designed this course with our other instructor, Prash, who's not here with us tonight, but Prash is a biomedical engineering PhD candidate here at UBC. He's also a Vanier scholar, so super impressive. And Ricky here, he has a background in engineering physics with a minor in math from UBC, with co-oping employment in software, laser physics, and data science. Ricky then went on to a master's in biomedical engineering. His research specialty from his graduate degree was in developing AI for feature detect and disease prediction in fetal ultrasound. He also worked at MDA as a software engineer for a year. Ricky, he's currently at Queen's University, located in Kingston, Ontario, for his MD degree. So yeah, enough from me. I'll pass on to you then, Ricky.
That's a very flattering introduction. Thank you, Olivia. Hopefully it didn't overhype too much, but very excited to have everyone here. Always excited to have more people interested in AI. I'm sure you'll all do great things in AI in the future. So this is a workshop that's introduction to artificial intelligence. I'll go over a bit of what it's about. It's not going to be your general like TED Talk, AI talk, where I talk about how great AI is. I think everyone here is already interested in AI. Moreover, it's more specific topics we'll discuss that might be technically useful to you. So some disclaimers to get out of the way. I have no conflicts of interest to disclose. Our funding is by UBC Biomedical Imaging Artificial Intelligence Research Cluster, and we're hosted by the UBC Artificial Intelligence in Medicine and Queen's Innovation Medicine Clubs. Special thanks to the National AI in Medicine Student Society Network across all the schools in Canada. Like Olivia said, this is a sort of informal. Feel free to ask questions anytime in the chat. I'll try to monitor the chat. Feel free to post any comments, memes, jokes, any questions you have. Absolutely, there's no pressure. So the agenda we have today, there's some boring intro stuff we'll go through. I'll go over some common AI misconceptions, translating some examples of AI in medicine. There's some current events that we might talk about, and then Prash has put on a few slides to discuss when we should not use AI and the limitations of AI, and we'll look at some examples in literature. And then if we have time, we'll move over some the technical data science section, which I think it's quite important for medical students to understand. It doesn't take a lot of math background to understand either. So really the objective is for you to understand AI on a broad level so that, for instance, you work on an AI project, you can discuss with engineers and researchers and not be totally lost. And we also want you to have a direction so that if you want to guide further AI training, you can do so. For instance, hopefully by the end of the course, you understand what this is. This is a convolutional neural network. Hopefully you understand what the circles mean. You don't have to understand math, but at least understand the intuition behind it and know that it's very good for medical image analysis, for instance, but very bad for analyzing serum analytes. Now, there are some potential roles in literature described for medical students. You can just be a user who's very proficient at using AI. This is like someone who, for instance, is good at using computers. You can be an analyst, someone who analyzes the use of AI, whether it's good or not for your field. This is someone who, let's say, screens for purchase of new computers to your department and understands if those computers are powerful enough for your application. And there's also a more pure engineering role where you're actually developing technical inventions. It's like you're actually building a computer for your department. So what we're going to do is that we're going to provide introduction for these first two roles, and then we'll show you a bit of what the engineering background looks like. If you're certainly interested, there are more resources, and these are the resources that are quite popular online. So the reason why we made this course is because we saw that there's a dichotomy in the AI resources out there. There are these more technical courses. The most popular one is Machine Learning by Andrew Ng on Coursera. It's a great course. If you're interested, feel free to take it. It's a like 30, 40-hour commitment, but he does go in quite deeply into the linear algebra and the math behind it. And a lot of medical students, they go through, when they talk to me, they go through maybe 5 or 6 hours and they either get bored or they say it's not fast enough to get to the information they need for the specific project, right? If there's one technical course I recommend, it's this one, the UBC Computer Science 340. If you do want to get into the math and the programming, this is, I think, the gold standard for introductory AI courses. And then the absolute state of the art, Stanford has their online convolutional neural network course on YouTube. They show you some state of the art artificial intelligence architectures, but it's quite deep in theory. And then on the other hand, you have a lot of these TED Talks and these events where usually an AI expert who's very well accomplished comes up, but because they only have an hour or two, they say, AI is great. Here's some examples. AI is really great. You should all use AI. These are great for the public and for your first talk, but it doesn't give you enough details to actually pursue AI, we found. And anyone involved in development will tell you the devil's in the details, like knowing exactly what AI architecture to select, how to format your data, how to prepare your data. Those are all problems that people run down the line and that these seminars really don't prepare you for. So we made this course that's sort of in the middle. It gives you a nice introduction without getting too involved in the technical background. But if you do have any questions about more general applications or more technical detail, feel free to ask. I'm happy to try to answer. These are some buzzwords that have evolved in AI, and AI is a notorious field for using buzzwords. So hopefully by the end of this course, you understand what all this means, like what neural network is, what we mean when we say logistic regression, decision tree. And then if there's one thing that I wish was taught in medical school in terms of statistics, it's the idea of cross-validation when you're building models. There is beginning a shift of changing medical guidelines where they're using proper data science practices, particularly cross-validation. And you'll see this in later workshop lectures. Logistics, there'll be about 30 minutes of me talking, and then each session will come with a programming example. We'll give you a link to an online Google Drive document, which you can clone into your local Google Drive, and you can program right in your browser on Google Collaboratory. Everything's available on the website whenever you're lost. And like Olivia said, Tuesdays 6 to 7 Eastern, I think, except next week and except March 30th. I think UBC has some big exams this week. But just check the emails and check the Slack and join the Slack. The Slack is, feel free to chat in Slack, post stuff in Slack. Announcements will also be in the Slack. It's a flex slide. I'm not gonna go over me, but Prash, he actually helped a lot. He's not here, but he helped a lot with developing the Python notebooks that will be used to give some programming examples. And he's very well accomplished. He had as an engineering science degree from Oxford. So he's certainly the technical backbone of this course. Not to discredit other organizers, Zoe, Rohi, Olivia, and Kevin also helped organize this course. They help a lot in the background, make sure everything runs smoothly. Okay, so now the boring logistics stuff's out of the way. Let's talk about some technical ammunition for you to understand AI so that when someone comes to you and they want to talk to you about AI, you have some good details that you can provide some answers. So specifically what AI is, there is a technical definition. It's something, a machine or system that can analyze environment and complete a task. But there's this really bad part of the definition where it says that the task has to require natural intelligence. So what the heck does this mean? Well, it's not very clear in the literature. It's any sort of task that is complex. There's no direct link from one step to another. So in the beginning, things like character recognition was quite complex and considered AI. But now people have very clear mathematical models for character recognition. So some argue it's not considered AI anymore, right? So if there's a robot that only passes butter, it's not considered AI. But Siri, now in the most recent iteration, people consider it AI. So AI is anything that can complete a hard task. Now, but the big buzzword, the new kid on the block in the past 20 years is machine learning. So to make sure our ducks in a row, the definition of machine learning is a subset of artificial intelligence. Artificial intelligence is something that can sense the environment and then perform a task. Machine learning is a particular way to apply AI so that every time you complete a task, you review how well you did, and then you update how you complete a task. For instance, an artificial intelligence robot will shoot a basketball in a hoop and calculate exactly where the hoop is to shoot the basketball. A machine learning program will shoot the basketball and see how much the basketball missed, and then shoot the basketball again. So deep learning is another subset of machine learning where the intermediate calculations to update that decision-making process has many individual layers. There's no threshold to how many layers is considered deep learning. Usually 3 or 4 layers, I would consider that deep learning. But deep learning, you can just think it's machine learning with a lot of intermediate steps that are very mathematically complex. Okay, so these are just some definitions to get out of the way. So some misconceptions. There's a big misconception that AI is going to replace physicians. Some people have strong opinions on it. My opinion, and I think a lot of experts agree, is that right now I think there's 0 automated AI medical applications. Last time I checked in 2019, I think there is still 0. So AI still requires humans, it requires supervision from humans. Secondly, AI is not completely objective. There is a lot of bias in AI because humans build AI. The data we use to train AI is selected by humans. So there is bias in AI applications and they will make errors. So we won't see things like AI court judges for a long, long time. Lastly is that AI is this magical black box that can just figure out your data. If anyone's watched this is from one of my favorite TV shows, Westworld. Season 1 is one of my favorites. Season 3 is so-so. Anyway, AI can't just figure out your data magically and give you an output. You have to make sure you prune your data really, really well, prepare it well, define your problem really well, and then AI can optimize mathematical models for it. And we'll see some examples of this. So these misconceptions usually are ignored in a lot of talks because it sort of drives some limitations in AI, but these are very important details that are the bane of existence of every AI researcher. For instance, preparing data really, really well is actually a very hard task, but you can accomplish some great things when you're able to overcome this challenge. So some motivation of AI use, I don't need to beat this to death, but there's a lot of money going to AI. Things are faster, more automatic, and there's greater complexity. So the question is, what does greater complexity actually mean? So this is an example from chess. So when chess just first started, AI defeats a human. So that's the first step. The second step is that humans will study the AI to see what the chess program does to beat the human. And then in this way, the chess program gets better, and then the humans get better. And then both fields, both the human analysis and AI analysis advance. So that's what we mean by incremental complexity. By studying AI, developing AI, we also improve human understanding of things. And this is very relevant in medical imaging. So the question is, why medical students? Well, there's always fragmentation in knowledge. Some engineer can come and show you, hey, this is a really cool technology. And then a physician will say, well, this is hard to use and we'll never use this. Otherwise, a engineer can say this is a cool application, and a physician will say, well, this will never work and you didn't prepare the data very well. So there's no way that AI can solve your problem. So hopefully you will be a combination of these two. And I put these two characters into a AI blender, and this is what I got. So you can take this image and do what you want with it. Now, there's also a lot of misinformation out there, particularly on social media sites, especially this guy, who says there'll be self-driving cars by the end of 2019. And there's also the word quantum thrown around everywhere. So being knowledgeable in this space is very, very beneficial. And you are all going to be leaders in healthcare and leaders in technology. So having a good aptitude to understand what's legitimate and what's not really helps AI move smoothly into medicine in the future. So that's all I have for the intro technical stuff. Now, we'll take a 1-minute question break. If anyone has any questions, feel free to type in chat, or feel free to speak up and ask, or use the raise hand function. Never used that before. Right. Well, so if there are no questions, we can move on and talk about some technical stuff. So the question is that when should you use AI for application? Because AI is great, but it's not magic, right? It's one of the many tools we have to interpret data. We have a lot of statistical tools, and AI is one of them. The question is, when is it appropriate? Because AI can get you really high accuracies, but sometimes these are fabricated, and we'll see in some papers later on. This is one example that Prash provided. This is a deep learning algorithm to predict aftershock patterns following large earthquakes, and they had good accuracy, and it was published in a major journal. And then there's more and more neural networks developed to predict this, but then they found that when you add a really, really complex network, you get really good accuracy. But when you have a really simple network, you have just as good accuracy, and it's more interpretable. So there's a question of how complex of a solution do you want to your problem, right? If something can be solved with something simple, it's much more interpretable by clinicians. So here's an example. So this is a plot of weight compared to days to stop smoking. And say a new patient comes in and wants to start smoking, and this is the data you have. Well, what do you tell them? Should you use AI to extrapolate this data? Should you use a basic linear regression? Should you just use a linear fit? Well, there are many methods to do this. And so, for instance, this is just a linear regression, fitting a linear line to this plot. And then, the classical statistical way is to extrapolate from this. But if we look, there are data points that fit this line quite well, and there are data points that don't fit this line quite well. So perhaps we need something more complex. But if we have something really complex, like say an AI algorithm could go through all these points at once. Well, this is like a 30-layer neural network. But when a new data point comes in, say a new data point comes in here, our algorithm won't be able to catch it because it's far too complex and far too overfitted for this data. And in this application, that type of AI, a highly complex AI, won't be useful. Now, an AI algorithm can only be used when you suspect there's a viable pattern or what's called a signal. So there has to be something on the very fundamental first principle level, so down to the biophysics, that something is happening within the data, that there is some relationship between the outcome and your input variables, right? And a good enough AI will be able to sense this pattern. So you also have to be clear what objective you want. If you want to just highlight a good odds ratio, what variables are important, you might not need AI. But if you want to complete a task like predict the risk of these patients, then you will need an AI application. AI application is good at predicting outcomes, but it's not the best at describing the data itself. I'll give you an example in a few slides. So you should not use AI when, for instance, a pattern does not exist, or a pattern is very simple. If it's a very, very simple problem, you want your solution to be interpretable. In mathematics, the most beautiful formulas is when a very complex problem is condensed into one line. You should also not use AI when prediction is not necessary. If you're writing a paper and your PI just wants you to observe some odds ratios and p-values for this data set, then you don't have to build an AI algorithm to predict the outcome from the variables. It might be impressive, it might be useful, but if your PI does not want it, that's not the goal of your project. AI is not the best solution for that. You rather have, say, a Pearson correlation analysis or a t-test. So a big problem in AI is that a lot of people try to use AI with very limited data. AI, because these relationships are so complex, we need really good statistical power to sniff out these relationships. So we need a lot of data in AI. The question, how much data do we need? It's still a matter of debate. The rule of thumb is 10 times the number of variables. But then when it gets more complex, you'll need more complex data. For logistic regressions, 10 times the number of variables is a good rule of thumb. But for something like a neural network, usually people have hundreds or thousands of data points. So now, for instance, this is an example of a data set where a simple AI algorithm might not be able to predict anything, because you see there's this step right here. So if an AI algorithm, let's say I think the best fit line on a polynomial will do something like this. But you won't able to, every patient within the step will have absurdly high error. So you have to be very clear of the nature of your data. This is especially problematic when it comes to categorical data. AI really likes continuous data, right? Binary data it's not impossible to deal with. A lot of projects, all the projects I've worked on have binary data in them, but a lot of information is lost when things are just 0 or 1. Say, for instance, a good continuous variable would be number of pack years smoked. A not so good variable to analyze would be, do you smoke or not? Because someone smoking could have smoked for 60 years compared to smoking for 1 year, and they will still answer yes. So you lose a lot of information when you get to binary data. So this is Prash's definition, which is a little bit more technical. An AI is an algorithm that can identify patterns in the data, use it to create a model, and then predict it on new data. This is what AI is used for in medicine a lot. You see a lot of applications. For instance, analyzing patterns in a chest X-ray and be able to predict if there's pneumonia. And recent AI can predict very, very complex things by using different degrees of complexity in their architectures. For instance, this is a CT scan of the iliac crest, and then there's also some synthesized ultrasound from a CT scan, and you can reconstruct some quite cool things using AI, but you have to use it appropriately. So since COVID-19 happened, pretend every one of these Lord of the Rings character is some AI project. There have been so many AI projects with COVID-19 trying to predict mortality, predict the survival if you're using a certain drug. And a lot of these did not follow best practices in data analytics, which resulted in this review paper where they reviewed a lot of prediction models and diagnostic models for COVID-19. And these models all use demographic data, the age, some sera markers, AST, ALT, and then some checks X-rays. All of them reported good accuracies, 0.85, 0.88. There's one paper that I'll rip apart in a few weeks that had, I think, 0.96 accuracy to be able to predict COVID from a cough alone. I was actually did not like that paper that much. But what this paper found that a lot of these publications did not have good definitions of their outcome, and they did not balance their data set correctly. They cherry picked to have a specific sensitivity and specificity balance so that their accuracy is high, or they were overfitted on specific application. For instance, they're only looking at chest X-rays of 18-year-olds in this certain region with a certain strain of COVID-19. Of course, your prediction algorithm is going to be 98, 99% when your data is that constrained. So one big thing to look out for when you're looking at data and where you're appraising papers is making sure that AI is developed on a diverse data set. Meaning that, for instance, if you want to predict the occurrence of a myocardial infarction, you should not just look at, say, people over age of 65 in Vancouver. Your model is guaranteed to be overfit. You'll have high accuracies. You might be accepted in some journal, but it's not going to be clinically useful because someone takes that model, bring it over to, let's say, Italy, and you have a completely different demographic, and you won't be able to achieve that same prediction accuracy. So that's a bit of skepticism that we have to present about AI. And there's a few tidbits there to foreshadow what we're going to learn in order to criticize these papers. I'll go over some key definitions just so we share a common language. So pretend there's this data set. Let's say we have a bunch of hockey players and we have their demographic data, what division they're in, and we have some clinical data of their oral temperature and their age, where they have exudates and lymphadenopathy. And our outcome that we want to predict is if they have group A strep. So these variables, say their name, the age, the division, oral temperature, in AI, we call these features. We don't really use the word variables that often. I've seen it interchange, but features is the main word we use. When we talk about feature selection, feature importance, feature detection, these variables are called features. Some people call it descriptors. Please don't call them descriptors. It just confuses the heck out of everyone. This, what we want to predict, we call this usually the outcome or the ground truth. And then each individual row, so let's say this hockey player, Stamkos, we call this an example. So this is one example. Matthews is another example. McDavid is another example. Some people call them samples. Some people call them items. I think items is the most confusing of all of them. So there's a question. Is this an issue with just external validity in a more diverse sample, or are there more variables diversity necessary to access the likely causal factors? Will the algorithm fixate on spurious relationships? So it is both. So it's certainly, we won't be able to, there are hundreds and thousands of confounding variables that probably are related to outcome, let's say group A strep. We won't be able to elicit all of them. So that confounding is always going to be there. And it's really hard to determine a straight causal relationship between something that's physiological. When we have a more diverse sample, we're really relying on the central limit theorem to save us, meaning that all of these confounding variables hopefully will let's say confounding variables like height, for instance. Okay, and this is distribution of height, here frequency. Let's say if we sample enough, the central limit theorem says that everything will be normally distributed. So which means that when we randomly split these patients into two groups, hopefully all these confounding variables will be able to evenly split, and that they won't affect our ability to measure the association of other variables. It's very hard to determine causal relationships even with AI. A lot of AI is used to determine correlational relationships and whether we can have really high accuracy correlations. Causal relationships, we need biological plausibility in the variables, and AI can help identify which variables are involved in that, but it's very difficult to do. So hopefully that answers the question. Okay, so a lot of people have seen this before, but for those of you that didn't, there's this hierarchy of evidence in biostatistics, where the higher you go on this pyramid, the more strong your evidence is. So at the very bottom is opinion pieces, and then case reports, and then you have these case control and cohort studies, and then on the very top of the pyramid, we have randomized controlled trials, and then systematic reviews and meta-analyses. So the question is, where does AI stand in this pyramid? So AI is definitely not on the bottom. An AI experiment is definitely not on the bottom. On the bottom is opinions and editorials. Unfortunately, they somehow catch the attention of media the most, not the meta-analyses. So machine learning and AI isn't a traditional control versus comparative study. For instance, we take a lot of data and we see if we can predict an outcome. Well, that's not exactly a cohort study either. We're not just looking at a group of patients and seeing if there's an association. We're running an experiment where we're trying to predict the outcome and seeing if our prediction is correct or not. So I would argue it's kind of in between a cohort study and a randomized controlled trial. We don't have the rigor of a randomized controlled trial of selecting patients, randomly assigning them, blinding everything, and then analyzing afterwards. But we're also not a cohort study where we just take some data and look at it. We're actually computing, trying to achieve a task and predict something with that data. So if someone asks where AI machine learning experiments stand on this pyramid, it's usually somewhere there. Now, so this brings a good question of what sort of statistics are we computing with artificial intelligence? Well, we know when we're giving a bunch of variables relating to patients, there are some descriptive statistics that are classic biostats. We're looking at the mean, the standard deviation, the spread of the data. And then there's statistics that are more like inferential stats, where we want to draw conclusions from that data. And traditionally, statistics, we use p-values, ANOVA or odds ratios to get these inferential insights into the data. For instance, we look at the p-value of age compared to COVID-19 morbidity. Now, the problem with p-values and problem with odds ratios is that p-values is just another variable, right? When we say age has a p-value of 0.05, what we're saying is that, well, age has the outcome between people of low age and high age are different. We're just saying that they're different. We're not saying what age we can use as a cutoff. We're not saying how predictive age is. We're not saying whether age is the most important variable compared to another variable, right? So p-value, it's inferential, but it's not predictive. And that's where machine learning comes in. We want to use things like the p-values, or even without the p-values, like age, whether they have polypharmacy, for instance, and a lot of different variables, and predict the outcome. So machine learning is really a really powerful form of inferential statistics, particularly predictive inferential statistics. So finally, I'll end with an example. So for instance, I'll show you an example of how these scoring systems were developed in the past, and an example of machine learning that a lot of people don't realize was machine learning. So this is the Curve 65 score for the mortality prediction for pneumonia. So what they did in the past was that they looked at some variables that looked to be really high, had really high association with mortality. For instance, confusion, whether they had a high respiratory rate, whether they have advanced age, and then they assigned a scoring system. And for reference, the key giveaway that this was manually assigned and it's not the best accuracy is that everything's a nice round number. In nature, it's very unlikely that associations will have a nice round number. So this scoring system, you add up this scoring system, and then you're given a mortality associated with that score. Now, this has I think sensitivity and specificity around anywhere from 60 to 80%, sometimes even 55%. So it's a wide range of sensitivity and specificity. It's a good screening tool. It's used in clinics all over the world. We're taught it in my cardio rest block. But this is quite outdated. And with machine learning, we can do a lot better with sensitivity and specificity. So this is an example. Next, I'll show an example of machine learning used in clinical practice. And it's not what you expect. It's not robots sitting in the hospital making decisions for the doctors. An application of machine learning, which is widespread, is something like this. So this is a pediatric head CT rule. When a pediatric patient comes in with a suspected head trauma, this is the flowchart that a lot of clinicians are taught. So you look at the Glasgow coma score, and you look at their history of a fracture. And if it's above if it's below 15, you move to one branch. If it's above 15, I think you don't, or if it's 15, you don't give them a CT scan. So, and then you look at their level of consciousness, whether they have an altered mental state, or whether there's a severe mechanism of injury. So this does not look like a machine learning algorithm, right? Machine learning, we expect a robot in a big black box and then some output like a predictor score. But this was developed with machine learning. So what they did is that, similar to the previous, the Curve 65 score, they took a lot of relevant clinical variables, but instead of computing an odds ratio and p-value, what they did is that they used it to train a machine learning model. So in particular, the machine learning model they trained was called a decision tree, where they take variables. For instance, let's say Glasgow coma score is one variable. If it's equal to 15, you go to one branch. If it's less than 15, you go to another branch. And then you look at next variable, let's say mechanism of injury. If it's suspicious, you go to one branch. Not suspicious, you go to other branch. You go all the way down this tree, and then you're given some sort of risk. So let's say this is no CT, and then this node, this child node is high risk, and you give them a CT. So what the machine learning algorithm does is that it'll shuffle these nodes around. It'll optimize the placement using some clever calculus, and it'll optimize the threshold. It just so happens that the threshold chosen was, I think, 14. So if it's under 15, you go to one branch. If it's 15, you don't get a CT. And then they created this flowchart. So this flowchart is a decision tree. It's a machine learning algorithm, and it's being used to evaluate patients in a lot of hospitals. and it's being used to evaluate future patients. And when people think machine learning, they think the last 2 or 3 years, androids, robots, but this was made in 2009, and it's in clinical practice. So machine learning is starting to be ubiquitous, but not in the way that we think, right? This is an example of one machine learning algorithm called a decision tree, particularly a classification and regression tree. One of the algorithms that we'll go over. It's very, very, very useful. There's some more advanced versions of this, which I more recommend you use if you have a project related to this. But this is an example of something that we'll go over in the next few weeks. Okay, so at this point, before I go to the program example, are there any questions? Feel free to ask any questions, any comments in the chat. If you have any additional insights, because of course I'm not the absolute expert in everything, also feel free to add in the chat while I set up the programming example.
I was just wondering, in terms of the these have been simplified to binary variables before the regression tree was applied. How are they deciding these, like where the cutoffs are? Is that just expert opinion? Do you know? I'm sure it's variable, but I've been curious about that for a bit.
Right. So some variables are continuous, the ones that they could help, like Glasgow coma score. I guess it's not entirely continuous. There's the binary variables, for instance, if there's a severe mechanism of injury, that was done based off, the variable was assessed based off your clinician judgment. So if the clinician, if the ED physician thinks that there's a suspicious mechanism of injury, of blunt head trauma, they'll give that variable 1. So there is still subjectivity in that model, and it's not absolutely perfect. So I know it's not a good answer, but they subjectively assign a threshold.
Okay, I just mean for like whenever it's saying like a respiration rate greater than 22 or something like that.
Oh.
Somebody's just handpicked 22.
Oh, I see. Are you talking about the old way of doing it, or the machine learning way of doing it?
Either would be fantastic if you have insight.
So the old way of doing it, I think they look at their data set and they set a threshold and see what gives the highest and lowest sensitivity and specificity, and they pick 22 for their data set. The new way of doing it is that there's some advanced calculus method. So for instance, a neural network will use a method called gradient descent, where we'll optimize that threshold to give us the highest sensitivity and specificity on a subset of the data. And we'll retry with another different subset, so that we're sort of shuffling around what we're testing the machine learning algorithm on to have the highest generalizability. So old way of doing it, it's sort of manual selection. New way of doing it is with calculus and optimization. Does that answer the question?
Yeah, and can that be integrated in like a regression tree or a random forest?
Yeah.
That sort of like optimization process?
Yeah. So random forest and regression tree does that automatically using a regression tree uses the CART optimization algorithm that will select a threshold that gives you the highest accuracy. It does it automatically. Okay, so what I have here is the program example. So I'm going to link in the chat. This is a sort of blank skeleton version. Feel free to follow along. If this was live, everyone is on the laptop following along programming. That's what we did last year. It was really fun, but it's a little bit harder virtual. But here, this is an example of the program example that we're going to run. And I'll share my screen and I'll run it also on my screen, and I'll walk through the first few steps we're going to do. Okay. All right, so what you can do, let's see. Oh no, okay, let me grant everyone access. Okay, let me try again. Does this work? All right, great, thanks. All right, so I'll give everyone a minute to look at what's in store. So this is using Google Colaboratory, which is an online Python programming environment. Python is by far the most popular machine learning programming environment. It used to be used to be some other, MATLAB was popular for a while and C++, but Python really has the most public support because it's open source. So what we have here, I'll just go through an intro while everyone's getting set up. So we have a data set available of breast cancer data. So these are breast cancer images with some features measured. For instance, the mean smoothness, the mean compactness of the image, the mean concavity, and we want to use these variables to try and predict if the cancer is malignant or not. So what we have to do, really Prash is the one we have to thank to set this up. So the first step we have to do is import some important libraries, because we're not going to programming everything from scratch. There are existing tools out there that can help us analyze this data. So to use this notebook, they're divided into cells. When you click a cell, you'll see this shaded highlight around the cell. To run a cell, you can either press the play button, or there's a hotkey, Control Enter. And you'll see it run. You'll see this loading circle of it running. And when it's done, if there's no error, if there's no output specified, you'll see the loading bar end. So let's run this first cell. So I'm going to select the cell, press Control Enter, and it runs the cell. So now the breast cancer data set is provided by the sklearn library. So all we have to do is say dataset equals load breast cancer, right? So if we run the cell, Control Enter in this cell, it just runs, but we don't know what it did. So what we can do is that we can tell Python to print out the contents of this data. So we say print dataset, and I'll run this again. So Control Enter. Right. So print spits out all the numbers in this data set. Oh yeah, no worries, no worries. If you have to leave anytime, feel free to come and go at any time. This is informal, it's for your information. So what we see a bunch of these numbers, right? It looks like these are labels, like the worst smoothness, worst texture, worst area, worst perimeter, but it's not very interpretable. So what we can do is that a very popular method to format data in Python is to use a data frame. So how we do this is that we want to convert this entire data set into a data frame. So we can do this by saying the command to do this is we've got to name our data frame. So I'm going to name it df equals PD. PD means we're calling the pandas library. So if you see in the top, we imported the pandas library as PD. So we're going to look in this pandas library, and there's a function called data frame. Right? So we have to specify our data set. So here it tells us what we need to specify. So we have to specify what our data is. So data equals data set data. We have to specify the column name. So columns equals data set feature names, because within the data set, there's this column called feature names that have all these labels. So and let's clarify this by, let's make it a bit easier by making a outcome column called label. So this is how we create a new column in the data frame, df square brackets label. And then I'll say it's equal to a column called target, because they have a column called target, which is whether it's malignant or benign. So and this, I'm not doing this from memory. I looked up what the data set is, how it's formatted, and what they're defined. For you, whenever you have a data set in the feature, you'll have your data set name. You'll import it as an Excel file. You'll know what the column names is. So you'll just say data set and then say outcome. Let's say you name your outcome column name outcome. So this is just loading a pre-made data set. Okay, so then we can look at what it looks like by calling the head command. So the head command will show us, get us a glimpse of what this data frame looks like. So I'm going to run this, and it looks like we have all these variables: mean radius, mean texture, mean perimeter, perimeter error, and then at the very end, we have label, which is whether it's benign or malignant. Okay. So now, what a lot of people like to do is called exploratory data analysis, where the first step, they want to just visualize their data on a nice 2D plot and see what it looks like, right? So here, this is, we're using the matplotlib library. This is a common method, and I didn't memorize this, but you can look up how to plot how do you have a scatter plot from a data frame on Google, and you'll see a lot of examples. So we're going to run a command called scatter equals ax scatter. And then let's say we want to look at the mean radius, right, compared to the mean texture. And then let's say we want to color it differently. So this is the command to color the scatter plot differently, and we'll color it by its label. Okay, let's see what happens when we try to run this. Okay, I typo. Okay, so this is, sorry, this is df. Right, this is what we have. We have mean radius compared to texture, and then different colors. I think purple is malignant and yellow is benign. So the way you look at this is you look at what's defined as 0 and what's defined as 1. But for interest of time, I looked at it, and purple is 1 is malignant and 0 is benign. Right. So this is an initial visualization. A lot of people like putting this in their publications just to show the range of the data. So we notice there is some delineation, but it's not exactly linear. Maybe it's curvilinear, but you can see when you add more variables, this gets a lot harder, a lot more complex. That's where some machine learning will come in, which we'll show in the next few weeks. So now, what can we do so far? So a cool thing that we can do is, so this is something that we put in here. It's a lot of programming troubleshooting to get this. None of this is mathematically hard. Everyone can figure it out. It's just a lot of looking up of what this specific programming line is. So what we can do is we can compute the mean, the max, and the worst benign smoothness. We just, let's see. Okay, I'm not going to run this up. I'm actually going to show you something else in the interest of time. What a lot of papers like is a correlation matrix. This is a really pretty figure to show a PI and put it on your poster. What this will do is we want to see how these variables are associated with outcome when we compute a linear correlation. So the command to do this is, let's say we'll name our correlation matrix core matrix equals df.core. So this will compute a correlation matrix. So if I run this, what happens? It does compute, but nothing happens. So we want to visualize it now. So we're going to have to make another plot. So similar to above, let's say I'm going to create a figure, plot subplots. I want to create a figure size. Let's say, let's make it square. Let's see, and then, sorry, typo somewhere here, there, right there. There's an equal sign right here. This is fixed size. Creates the figure, but it's empty. Now we got populated with that data frame. Okay, so to do this, we'll tell it to show the image of the correlation matrix. And then let's select color, cool color map. Let's select plasma. Now we have the heat map of the correlations of the variable. So let's say this is variable 1 and how it's associated with another variable 1. So now we want to add some axis labels to make this more interpretable. So let's set the x-axis as we're going to arrange by the dimensions of the correlation matrix. Let's see what happens. This always happens. Okay, and then we want to do, always make typos. We want to do the same with the y-axis. So let's say here, instead of x ticks, now we'll have y ticks, right? And now we have some nice labels. But now we want the actual variables. So to add the actual variables, we want to set labels. So we do this by setting x tick labels. And then we want to do it by the columns of the data frame. Right? And then exact same with the y-axis. So now this is much more interpretable. So what we have is a comparison between one variable to another, and we compute the correlation ratio. So perfect correlation means two variables are exactly correlated one-to-one. So for instance, mean radius correlated with mean radius is completely yellow, which means it's 1, which is expected. Perimeter and radius are highly correlated, which is expected. What we want in terms of analysis is to see how it's correlated with the outcome. So yeah, so we notice that this axis at the bottom is a lot smudged and all the text is mushed together. So there's some beautification code that we can add in. So for instance, we can tell the plot to rotate the x-axis by saying x ticks rotation equals vertical. Right? And let's add a color bar just to make it more interpretable. So we'll run it one more time. So here we go. Now this looks like a nice plot, like a great plot for a poster or even a publication. So what we have is this color bar shows us what's the most correlated and what's the least correlated. And we want to look at the outcome, the label. So we see that things aren't really that correlated yet, right? The best correlation is what, like 0.2, 0.25, something's 0.4, right? Smoothness and the texture error. And this is linear correlation. For instance, this is just seeing how much one variable changes linearly when another variable changes the exact same amount. So what this is saying is that by linear analysis alone, we're not able to predict the outcome very, very well. But as you'll see later on in later versions, when we develop this programming notebook further, machine learning can predict this very, very, very well. There's a prediction accuracy of, I think, about 97% that was published with this example by using machine learning. And I can tell you, if you're only using a manual scoring system with this, your prediction accuracy will be like 60, 65%, right? So this example, so this is where we'll stop our programming for now, but this is just to show you how we load in data, visualize it as part of exploratory data analysis, and then do some initial visualizations just to see how the data is related and if machine learning is a good application for this. For instance, if one variable was just one-to-one correlated and completely yellow, machine learning might not be useful, right? We can just use that variable to assess the patients. For instance, if I don't know, this atypical, if one of the variables was atypical mitotic figures on histology, of course, that's going to be very highly correlated because that's how we diagnose these cancers. So that's an example where machine learning would not be useful. Okay, so that's all we have for now in terms of our presentation and our examples. If there are any questions, feel free to ask in the chat. I'll stick around for another 5-10 minutes to answer any questions everyone has. Other than that, thank you everyone for coming. We'll post all this online as a video and we'll give an announcement email of the next session.
I have maybe a silly question because I've never used Python before. So with like the matplotlib thing, that's the library that you're using for this plotting, right?
Yeah, that's correct.
Is that like a pretty standard, like for Python, like are these things that are very commonly used?
Yeah, matplotlib is the most common plotting library used for Python. So it's useful to learn. Yeah.
Thanks.
Yeah.
Hey, Ricky, great talk. I have a kind of a general question, which is, you've alluded now to not everything necessarily needs machine learning. And then I think there is also the question of what you can sort of apply something fairly out of the box to versus having to build a more custom model for. And do you have an approach for deciding, like at what point when you're trying to solve a problem with machine learning, would you say, okay, I need to really make some modifications to existing algorithms or approaches in order to actually make this work with my data?
Right. So that's a great question. So we always have to have an initial discussion of what the gold standard is and what's good enough, because there are projects where let's say the top 10 machine learning architectures and 9 of them can achieve 90% accuracy. And if 90% accuracy is good enough, then we don't need to reinvent the wheel. We can just use the existing algorithms. So there's quite significant diminishing returns once you go above 92, 93% accuracies, because I think that's around the range where I would say it's good enough. We don't have to develop anything new. Because once you get higher, of course, it's a little bit different for different problems. Simpler problems, we want higher accuracies for, but for very complex problem, the issue of sensitivity becomes very important. If we're just making our model more complex to increase the accuracy, very often we're giving up generality, which means that we'll have 95% accuracy for this one application, but we'll lose accuracy when we're applying to new data. So in those cases, we would look at what's already out there. If the accuracy is high enough so that we're not concerned about sensitivity, otherwise we'll develop something new. So does that answer the question, sort of?
Yeah, I think it goes some way to answer it. Yeah, I sort of wonder about like there's different approaches where I feel like some machine learning approaches are more amenable to basically, if you have a list of predictors, then you can sort of plug and play. Whereas there's other approaches where you have to do a lot more fine tuning of the method's parameters. I'm sure it's stuff that we'll kind of get more into in later weeks, though.
Yeah, for sure. And a lot of it comes with simpler problems where there's a clear association. Usually simpler algorithms are completely fine, but very hard problems. For instance, I just work with a data set where we're looking at CT tumor scans and we're trying to predict the local control of the liver metastases. That's a very, very tough problem to look at texture-wise, and we have to create something totally new for that. So it also comes with the complexity of the problem.
Right. Thank you.
Yeah, no worries.
I had a question surrounding the feasibility of doing this on like a school laptop. Like, do you need big data, like big computers or access to a university? I don't know what you call them, but big computers in order to work with this size of data sets you're going to need to solve medical problems?
No, so not always. So the computational power required all depends on the complexity of your network. Usually with numerical data, usually depends on how complex it is. Usually, for instance, this is all numerical data. On a school laptop, on my own laptop, we can run this fine. When something comes with millions and billions of parameters, that usually, for instance, image analysis is much higher in complexity and requires high-powered GPUs. So generally, images, videos, surgical guidance, image prediction, that requires high intensive resources. Something like this, when you're just looking at clinical variables and you want to create a predictor, or if you're like that, the Pecan trial I use, they absolutely did not need to use a big server, $10,000 server. You can do it on your own laptop.
And then a second question I had, if that's okay. So I think like a classic example of sort of the image recognition machine learning is the recognizing numbers. There's there's a bunch of videos on YouTube like that. And a question that pops into my mind whenever you see the neural network used to detect numbers is, why not cheat a little bit and put some of the pieces of the numbers into some of the nodes in the network, and then let the network just decide, like add some like a line of nodes before, a line of nodes after, and let the model weights determine these sub pieces of the numbers and then let it connect at the end. So I guess what I'm trying to ask is, are there ways to pre-specify what some of the nodes in your neural network are going to mean and be used for?
Yeah, absolutely. So there's methods called attention learning, where you tell the neural network to pay attention to this area of the number if you know this area is like definitive. And there's also methods called transfer learning, where you transfer over some known knowledge to the network. And I actually highly recommend it. If you're approaching a clinical problem and you already have part of the answer that you know is correct, why do you have to create a neural network that tries to figure out? If you put that in, then that part of the mystery is already solved. The neural network can solve with higher accuracy the other parts of the mystery. So that's actually a very, very good point. And transfer learning is something that is quite valuable and quite useful. Of course, with a lot of medical problems, because we're not certain about a lot of things, it's hard to transfer that known knowledge beforehand. But if it's possible, like with numbers, Absolutely. Get part of the number first. It'll help your network, higher accuracy, better performance. Okay. Yeah, if there are any other questions, absolutely feel free to post in the Slack, email. Slack is probably the best way to communicate. Otherwise, Olivia, take away.
Yeah, I guess we're at 7:02. So yeah, thank you so much everyone for coming again tonight. Yeah, can you post the link to the Slack? Yeah, yeah, give me a second. Everyone's free to leave if you want. I'll post the link to the Slack, and I'll also post the slides to these talks are on our website. So I'll post that as well in case if you want that. So give me a second. Here's our website. So you can look for the slides there, and here's our Slack. Yeah, other than that, have a